Okay, in this video I'm going to talk about electric fields. So an electric field exists because this is a field force, right? So a field is a region of space around a charged particle. So it's a region of space around a charged particle. Okay? So when another charged particle enters into the field, then the force arises. So when another charge enters the field, a force arises. Okay? So we can define an electric field mathematically, okay? So, and the way that we do this is we imagine, okay, let's just say there's this like big charged object. Like it's not a point charge, it's like, you know, a lot of like electrons or protons or whatever built up on it. And we could say that's some big letter Q. When we use the capital letter Q means that it's not just a point charge like a proton or an electron. It's like something that has like a massive charge as a result of a lot of protons and neutrons, but it's really the same thing, okay? So this thing has a field around it where this force could exist. And let's just say I brought a particle close, okay? And our test particle is always considered a positive particle, and that's why I draw it as positive. And we say the test particle, we write it with this like Q sub naught, right? So the electric field is defined by, and we write electric field with the capital letter E, okay, or you can write it like this too, either way. I kind of go back and forth on how I write my capital letter E's, is equal to the force exerted on some point charge in that field, okay? So the electric field strength at that location is for some point charge, okay, and it's relative to the force. So the magnitude of an electric field, okay, is force over charge, right? So we've got force over charge. So the unit is a Newton per Coulomb. Okay, now an electric field is a vector. So an electric field is a vector, right? Because it has a direction. And the direction of an electric field is defined by the force that would be exerted on a positive test charge particle, right? So if we have this scenario where I've got a big positive thing, right? And I were to put a positive test charge over here, the electric field would be in this direction, right? Because it would be the force, the direction of the force on this thing would be in that direction. So the electric field line is in that direction. Okay, now in the other case we have, let's say we have got a big negative object and we put a positive test particle over here. Well, the force on this thing, it's going to be in this direction, right? So the electric field line would be toward this thing. And you know, good convention to remember is that electrical field lines always point towards the negative or away from the positive. So E point towards positive test charge. Okay. Or that might be a little bit confusing. Let's say it like this. Let's say electron field lines point away from positive charges, point away from positive charges. Then we don't have to think about the test particle at all. And they point towards a negative. Okay, then we don't have to worry about test charge or anything there. We just know if you've got a positive thing, the electric field line is away from it. If you've got a negative, it's towards it. Excuse me. Okay. So there's another way that we can also calculate electrical field lines, and this is because of the and we can relate it to electrical force. Okay, so remember that force electric, the equation for that is K equals Q. In this case, we would say the test charge times the big charge all over R squared. Okay? And remember that we just also defined electric field as being force electric divided by Q sub naught, right? So I could divide this whole thing by Q sub naught, and it would cancel, right? So we can calculate the strength of the magnetic, or the strength, excuse me, of the electric field without a test charge being present, okay? Without having a magnitude of that. So the force, or the electric field, can also be calculated equivalent to K, what's exerting the charge, or the charge of the object that's making the field, all over how far away from you are from that thing squared. This is a lot more practical way of calculating an electrical field, because then we don't have this like imaginary test charge that we have to deal with. Okay, so the electric field strength is dependent on two different things. It's dependent on the magnitude of the charged object that is making the field, which makes sense, right? So think like a magnet, you know? If you got a really strong magnet, its field is going to be stronger. And then again, how far away you are from it, okay? So this, again, is a lot more practical because the electric field exists even if there isn't a test charge present, okay? Now, when we draw electric field lines, again, like I said, remember they point towards the negative or away from the positive. So if we draw it like this, if we have a charge, it's actually a 3D field, right? There's like this halo around it, you know, but just as in ease of representing, we would, you know, put it like this, you know, and they're kind of radiating out. I know that's kind of a horrible picture. All right, and then you would have positive, and they would be doing the opposite, right? Okay, pointing away. So the field is all around. It's three-dimensionally around, okay? And we have a couple of rules for drawing electric field lines, okay? So, again, I've already mentioned the one about they begin with a positive and end at infinity, or they begin at infinity and end at the negative. And that's really, they point towards negative and away from positive. Okay? Now, another rule is that the number of lines is proportional to the magnitude of the charge. So the number of lines you draw is proportional to the magnitude of charge. And you know, usually this is just something that's visual. So if we look and we say, like, let's say this charge is a lot bigger, there'd be a lot more lines, you know, and just by visually looking at it, you can see that this thing's electric field strength is bigger than this, just because there's more lines. The other thing is that field lines never cross. Okay, and so when you have more than one charge next to each other, you can create like a dipole. So if you have like a positive charge and a negative charge like we do up here. Here, we're envisioning they're completely separate. But here, let's say they're like next to each other in space, right? So you're going to have sort of this situation where the field lines kind of combined. And oops, that was a horrible job of doing that. You know, sorry, let me fix it. You know, and they're going to be doing this. There's like a combination of what is happening. You know, these field lines are pointing towards. Okay. Okay, and then here you're going to have field lines in. Okay, so just keep in mind that they will interact with one another. Okay, so those are a positive and a negative. If you have like charges, remember they're going to the field lines actually repel each other, so they're all going to kind of look like this, you know, pushing away from each other. Okay, and you're actually going to do a lab, you're going to look at this and actually be able to look, kind of define like what are the electric fields in this space in between, or like in this space right here. Okay. Now, one more thing that I want to discuss really quickly is an idea of electrical fields in a conductor. Okay, actually, you know what? I'm going to save that for the next video.